Okay, I expect if you're watching this video, you already know what the STEP examination involves, the 6th term examination papers. They're exams, originally that were, I think, devised by Cambridge University for admission to Cambridge. A lot of other universities also use them now as part of their offers for mathematics programs at university. Sometimes you will have to do STEP and have to do well in it. Other times it's just one of a number of things that you can do. But I know there'll be a fair number of people out there preparing for STEP, and actually also just people who are interested in maths. If you're doing A-level maths, especially further maths, then doing some of these STEP papers as you're going along with your studies is very, very enriching thing to do. Really can push you to do something a little bit different, a little bit harder. If you are new to them, Step 1 and 2 are usually aimed at the level where people who've done all of the content of A-level maths can access those questions. Step 2 and 3, if you've done all of maths and further maths. Although because different exam boards have slightly different syllabuses, the STEP exams do have their own syllabus. So it may be that even if you have done a full further maths A-level, then you can't do everything that's in those STEP papers, especially when you get to some of the mechanics or the statistics. But we're going to start with some Step 1 questions. If you're doing further maths, then you're towards the start of the course. These are great things to have a go at, actually some of them you'll still need to be further on in the course, or if you're doing single maths and you want something harder, they're great problems. Each problem is a 3-hour paper, and you're only meant to do 6 questions. Well, you can do more than 6 questions, but you just get marks for the 6 where you do best at. And so you're only ever really expected to do 6 questions at most. If you got all 6 right, that would be an incredible mark at STEP. You can actually get a good grade at STEP by only, if you've got a couple of full questions and some parts of other questions, you can still get a good grade. So each of these videos, I'm going to just focus on one single question. And we're going to start with question 1. And the people who set STEP always say that that question 1 is meant to be accessible. Right, now they mean something quite specific by that. They don't mean easy. They just mean that question 1 never really requires you to know a whole lot of maths. Right, usually it's just there's it might have been algebra. There's a lot to think about. It's going to be a tough question, but it's not going to involve anything from really far into the A-level course. So if you're at the start of your A-level studies, actually doing all the question 1s from the STEP papers is quite a good place to start. And once you have studied a bit more of A-level maths, you can then have a go at some of the rest of the papers. I'm going to assume as well that you can download these papers. I'll try and put a link somewhere, and you can see this one's June 2016. So if the questions are not, it's going to be hard for me to have the questions visible as well as the answers the whole time. But we will have a look. I'll try and leave the questions somewhere visible. The first part says, for n equals 1, 2, 3, and 4, we've got these functions Pn and Qn defined by these fairly daunting-looking expressions. Okay, we've got this one here, lots of brackets and n's in the exponents, and we've also got this division. Now it says show that Pnx is identically equal to Qnx. Remember, the 3 equal signs means identically equal, so equal for all values of x, not just some. And now the thing that's nice, it says just show that in the case n equals 1, 2, and 3. So we actually don't have to do it for a general case. In fact, it's going to be not true for n equals 4. Okay, so let's have a look at this. So P1x and P2x, we can replace all the n's in the expressions with 1. So I think I will start by just doing that. And a lot of STEP is really just following the instructions and following some of your mathematical instincts. And the more these you do, the more they will develop. So x plus 1 to the power of 2n. Now if n equals 1, that's just 2. Okay. Now minus 2n plus 1, so that's 3, I don't need the brackets then, times x squared plus x plus 1, now to the n minus 1, but actually that's 0. Okay, so anything to the power of 0 is just 1, so in fact this whole term here is just 1. Okay, so I've got x plus 1 squared minus 3x. Now given that I'm trying to show that's equal to something else, I think it makes sense for me to try and simplify this here. So I get x squared plus 2x plus 1 minus 3x, which is equal to x squared minus x plus 1. Now, we need to show that that's the same as q1 of x. And q1 of x, well, that's x to the 2n plus 1, so that's x to the power of 3 plus 1 divided by x plus 1. So I see you don't need to know too much maths here, but this is something from very early on in the maths courses, which would be to do a long division of polynomials, x cubed plus 1 divided by x plus 1. So that's something you'd learn at A level. But we may also be able to get away without doing the long division formula, and I'm going to try and do that here by sort of knowing the answer, because I know that if this division is going to work out and it's going to give me this, it's going to have to divide exactly. So actually x plus 1 is going to have to be a factor of the top here, x cubed plus 1. Okay, so I kind of know that in advance, but you could also do this as a long division. There's often different routes through a step problem. Okay, but I can just try then to factorise the top with a big hint as to how it's meant to factorise. So it would have to be x plus 1, it would have to have an x squared to give us this x cubed term. I would add x squared, but there's no x squared in here, so I'd also need to subtract an x squared, which I can achieve by doing minus x, because then minus x times x is minus x squared. But then I've also got a term introduced here, minus x plus 1, which is, times the plus 1, which is minus x, so I need to add in the x because it doesn't appear here. I can do that by adding 1, and conveniently that also gives me the plus 1. Okay, so I've got that it's x plus 1 times x squared minus x plus 1, and again, if you really are thinking about what's going on here, you should already know that that's going to be what the factor is that's going to come out, because it's the answer that we've got up here. Now, that might feel a bit like cheating when you first start thinking about this, but it's actually good mathematical problem solving. Okay, this is a perfectly valid method here that we've used, which is to show the factorization, and then we can just sort of show that they've cancelled out, and we've got that that's the same as x squared minus x plus 1, which is the same thing as p1 of x. I could use 3 equals for all of these as well, because it's an identity. Okay, so we've done the first part. The other thing you notice about step questions, these are meant to take, each of these questions is meant to take you half an hour, so it might take me longer even because I'm talking about it and explaining it as we're going along, but we'll see. So there's meant to be quite a lot of work. We've only got a tiny way in. Now, let's do the same thing then for p2 of x. If I look at p2 of x, that would give us x plus 1 to the power of 4 minus 5 times x squared plus x plus 1, this time all to the power of 1. Okay, so again, I think we need to multiply that out. Next thing that step really tests is, are you fluent in algebra? Can you, I said the question 1 often doesn't have so much like hard maths in it, but it requires you to be really quick with algebra, and the more tricks that you can just get on with quickly, like this one, x plus 1 to the power of 4, it's a binomial expansion, you've got to multiply the brackets. If you can get quickly to the correct binomial expansion here, x to the 4 plus 4x cubed plus 6x squared plus 4x plus 1, then you save yourself a lot of time, and it's fine just to write that down if you knew what it is. These coefficients, remember, come from Pascal's triangle. I don't have time in this video to go through every topic that we need, but look at binomial expansions if you don't know what that is. So we now do minus 5x cubed minus 5x squared minus 5x, and if we collect all the like terms together, we've got an x to the 4 plus 4 minus 5, so that's minus x cubed plus 6 minus 5, so plus x squared plus 4 minus 5 gives us minus x. Okay, so that's p2 of x, and again we can play a similar trick that we did before with q2 of x. q2 of x is going to be x to the power of 2 times 2 plus 1, so x to the 5 plus 1 divided by x plus 1. And again, actually, you can almost just cheat here, I think. Like, we know what the answer's got to be. Now, I would check as you're going along though, because if you're wrong, it's very embarrassing. Okay, but given that, you know, we have the same structure as we had before, this must factorize as x plus 1 times x to the 4 minus x cubed plus x squared minus x, all divided by x plus 1. Otherwise, there's something wrong with this question. But do just go through and check that when you multiply this out, you do get this. Okay, and I'm a good student, so I went back at the end of this video, checked my answers, and realized that I made a slight mistake. Here it is. There should have been a plus 1 here that I missed out from here to here. So there's also a plus 1, and the plus 1 that appears in the brackets here. But otherwise, argument, everything else, all absolutely fine. So I will let myself from earlier carry on. So that's b2 of x, and that's great. Now, right, what about the third one? Let's also show that it's true for n equals 3, so I need to look at p3 of x, and again, now the algebra is just getting a bit messy here, but again, it's kind of how step problems go. Don't worry if you've got a bit more algebra than you would usually. X plus 1 to the power of 6 minus 7x times x squared minus x plus 1, all squared. Again, we've got a binomial expansion here, so we might just need, we need the sixth row of Pascal's triangle for this one. So we had the 1, 4, 6, 4, 1 that we needed here. This one has the coefficients 1, 6, 15, 20, 15, 6, 1. You should be able to get to that pretty quickly. Some of you may even memorize these coefficients, I don't know. So we've got x to the power of 6 plus 6x to the 5 plus 15x to the 4 plus 20x cubed plus 15x squared plus 6x plus 1. And now for this stuff, okay, I've got minus 7x. Now, so there's lots of just little bits of algebra that are useful in STEP. You know that, let's just do this as an aside. Okay, you know that if you do a plus b squared, you get a squared plus b squared plus 2ab, right? Now what if you do a plus b plus c squared? Now you can just multiply this out and you can check that this is the case. We get something very similar, okay? We get all of the individual terms squared. If you think about multiplying this by itself, all of those terms must appear, and still we get all of the terms like a times c, b times c, a times c twice. So I get 2ab plus 2ac plus 2bc. Yeah. If you think about it, this would be true if you did, a plus b plus c plus d squared as well. Okay, we'd have a squared plus b squared plus c squared plus d squared, and we'd also have 2 times all of the terms like a times b, a times c, a times d, b times c, b times d, and c times d. So we can actually extend these kind of expansions from something that's got a binomial to trinomial to higher. So there we are. I should now be able to, I'm going to have to use another line I think. Let's take that minus 7x, and we can use this result. So what do I get? I would get multiplied by x squared squared minus x all squared, which is plus x squared and plus 1 squared, and then I get 2 times all of the cross terms, so 2 times x squared times minus x, which is so minus 2x cubed, the x squared times the 1, so that's 2x squared, and the minus x times the 1, so minus 2x, and then we just have to simplify all of this stuff down. I'm just going to be a little bit messy here and multiply this out, just this bit on its own. So I've got minus 7x to the 5 minus 7x squared minus 7x plus 14x to the 4. I could probably combine some of these things. Minus 14x cubed plus 14x squared. So let's get rid of that now. So when we combine all these together, I've got an x to the 6, I've got 6x to the 5 minus 7x to the 5, so that's minus x to the 5. I've got 15x to the 4 and 14x to the 4, I think that should be a minus. Oh, and it is, and I've just realised, again, be very careful, be more careful than me. I've already made a mistake, but this should actually be, I've miscopied something here. This one should have been x squared plus x plus 1. So actually that makes all of these, that just makes all of these terms positive, so it's not too hard to fix. So actually that one is minus 14x to the 4, and this one is minus 14x squared there. So we get plus x to the 4. Actually, one of the reason I could tell that I'd made a mistake was because this has got to follow a similar. I'm expecting a similar pattern to what's gone before. Okay, now better just to avoid those mistakes, but we have to stay alert to these things. 20x cubed, and then we've got and this was cubed as well. Minus 7x cubed minus 14x cubed, so that's minus x cubed, 15x squared, and then I've got minus 14x squared, so that's plus x squared, and then I've got 6x minus 7x, so that's minus x, and finally I've got a plus 1. Okay, so a bit of algebra, but we can do it reasonably quickly, and we just got to try and avoid making mistakes, which is hopefully easier when you're not doing it and recording it. But we always, little algebraic errors are inevitable. You shouldn't be too, you've got to try and avoid them. But the main thing is that we spot them and then we correct them. So that's P3 of x. So Q3 of x. That's equal to x to the power of 7 plus 1 over x plus 1. And now I kind of, know my trick here, which is just to say that this is, if I've done everything correctly, this is kind of a good check. This method, my slightly cheating method here, a good check that this is correct, because it must also factorize like this if this is going to work. Okay, and you're allowed to, you'd be allowed to know that x plus 1 is a factor of this, and factorize it like that. So that's fine. So we get exactly the same thing as before, exactly the same thing as P3 of x. So we've done a whole page of working here, 16 minutes into a video, and we have got down as far as here in the question. Remember, 30 minutes for a full answer to the question, and it is quicker if you're not speaking at the same time. Okay, so now it says show that this does not hold in the case n equals 4. So we need to look at n equals 4 and show that we don't get the same thing. So let's have a look at this. P4 of x, that would be x plus 1 to the 8 minus 9 times x squared plus x plus 1 to the power of 3. To the power of 3, yeah. And then Q4 of x, that would be x to the power of 9 plus 1 divided by x plus 1. And this is a point where you really have to make a decision. Are you going to do the algebra and show that you get different things in these two different cases? You can do it, you can multiply this out, but it's a lot of work. Now, and showing that the two expressions were the same, we did want to do that. But showing that the two expressions are different, there's really no reason to do that. Okay, so if I want to show that P4 of x is not identically equal to Q4 of x, all that means is that these expressions are not the same for every single value of x. To show that they're not the same for every value of x, I just have to find some value for which they are different. Right? So let's just try plugging in an easy value and seeing if we can just show that it's not the same, right? So I think my first instinct might be just to try something like 0. Okay. What about trying P4 of 0? What do I get? I get 0 plus 1 to the 8. So that's 1 to the power of 8 minus 0 times something, so just 0, so it's just 1. And Q4 of 0, that's equal to 0 plus 1 divided by 0 plus 1, that's also 1. Okay, that was a bit annoying. They do agree for 0, but that doesn't mean they're the same expression. Okay, it just means that they happen to coincide when x equals 0. If they're not going to be the same for all values, it's very unlikely we're going to find many more points where they're equal. Okay, so let's just try another value. Right? What's the next easiest thing we could do? We could try 1. Okay, P4 of 1. And let's put 1 into 1 plus 1 to the power of 8, that's 2 to the power of 8 minus 9 times 1 times 1 plus 1 plus 1 to the 3. So 9 times 3 cubed. So the non-calculator paper, so we have to be able to work these out. 2 to the power of 8 is 256. 3 cubed is 27, times another 3 squared takes us 81, 243. Okay, so that gives us 13. Okay, now let's have a look at q. q4 of 1, that's 1 to the 9 plus 1, so that's 2, and divided by 1 plus 1, which is also 2, which is 1. Aha, okay, so when I put 1 into P4, I get 13, and when I put 1 into Q4, I get 1. So actually, we can deduce then that P4 is not identically equal to Q4 of x. There's at least one value where they disagree. Much quicker than going through all of the algebra there. Right, okay, so we've done part 1. We've done some fairly complicated algebra, but it's all been quite standard so far. There's nothing, we haven't really had to think too much beyond applying A-level techniques. And this is how a step question will often be framed. We've got a part 1 and a part 2. And unlike in a lot of questions you might be used to, where part 1 and part 2 can be just two different applications of the same thing, or not even necessarily related at all in a GCSE, part 2s in step questions are very likely to follow on in some way from part 1. Okay, so we'll have a look at part 2 here, and we should be just on the lookout for forms that are the same, ideas that we've already been using that we can use again here. Okay, so part A here, express 300 cubed plus 1 divided by 301 as the product of two factors, neither of which is 1. Okay, so we've got 300 cubed plus 1 divided by 301. And what we should notice about this is that this has a kind of similar form to these Q polynomial, these Q expressions, the Qn expressions that we've just been looking at. Okay, and in fact, if we were to have a look at it, well, clearly, if you put x equals 300 into Q, you get something that looks a bit like this. And if we match up the exponents, we'd have to have 2n plus 1, which is 2n plus 1 being 3, so it would be Q1 of 300. Okay, so this expression is exactly the same as putting the number 300 into the expression for Q1. What did we prove in part 1? We proved that Q1 is equal to P1 for all values of x. Okay, so this is also equal to P1 of 300, and really, if that's not useful, I have no idea how we're going to do this question. This must be something that we can use. Okay, it's not obvious why at the moment, but I guess we'll get there in a second. Okay, so P1 of 300, let's just plug it into the definition. Right, so it's 301. It's x plus 1 to the power of 2 times 1, which is 2, minus 2 plus 1, 3 times 300, so minus, let's just write that out, 3 times 300, and then multiplied by something to the power of 0, so that's it. Okay, so we've got 301 squared minus 3 times 300. What do we do with that? How do we turn that into a product of two factors? Okay. Now, something that comes up all the time in maths, in step papers in particular, difference of two squares, using that for factorization. Okay, a squared minus b squared, we must know that that's equal to a plus b times a minus b, and in a step paper we've really got to be always on the lookout for those factorizations. And this is in the form of a difference of two squares. Perhaps not quite obvious that this second one is a square, but 3 times 300 is 900, which is 30 squared, or you can see you've got 3 times 3 times 10 times 10. Okay, so we've got 301 squared minus 30 squared. Using the difference of two squares, that's 301 plus 30 times 301 minus 30, so that gives us 331 multiplied by 271, and there we go. We have done exactly what we've been asked to do there, which is to express this thing as the product of two factors, neither of which was 1. Wasn't obvious at the outset that that strategy was going to be successful, but did become so, as we went on. Right, so That was part A. Part B, and actually once you've got part A and you see how it relates, part B again, I'm expecting this to be the same sort of thing, just a little bit harder, but we'll see how it goes. So it says express this thing here, 7 to the power of 49 plus 1 divided by 7 to the power of 7 plus 1 is the product of two factors, neither of which is 1, each written in terms of various powers of 7, which we should not attempt to calculate. So just a clue here, it's saying just use the structure, don't worry about the numbers exactly, just show us the structure, show us that you can see how this relates to what you've done before. Okay, so we look at the same, we're going to do the same thing as we've done here. It's got to be one of these Q expressions, and if you just look at the form of the expression, well, it's got to be 7 to the power of 7 in place of x, right? And 7 to the power of 49, let's write in the margin here, 7 to the power of 49, that's 7 to the 7, all to the power of 7, okay? So, this is the same thing as 7 to the 7, all to the 7 plus 1, over 7 to the 7 plus 1, and that then is Q3 of 7 to the power of 7. It's exactly that Q expression with n equals 3 and x equals 7 to the power of 7. Okay, so that's the same thing then as P3 of 7 to the power of 7 by what we showed earlier, and P3 of 7 to the power of 7 would be 7 to the power of 7 plus 1 to the power of 6 minus 2 times n plus 1, so that's 7 multiplied by x, which is 7 to the 7, multiplied by x squared, 7 to the 7 squared, plus 7 to the 7 plus 1, all squared. Okay, so this is looking a little messy, but maybe it'll be okay, because it's tempting now to start trying to multiply this all out, or but you really can't do that, because we have to try and copy the structure that we've learned from the previous parts of the question. Step questions are often trying to teach us something about how to solve the later parts of the questions. Right? They're actually trying to help you through the later parts with the earlier parts. So we've got to try and just see this as a difference of two squares. And if you look at it carefully, it is. Look, it's 7 to the 7 plus 1 to the power of 3 squared. By the way, a lot of people ask me about brackets. There's no difference between square brackets and ordinary brackets, right? It's just I'm just trying to distinguish. This one goes with this one, and this one goes with this one. But you can use whichever type you like. And 7 times 7 to the 7, that's 7 to the 8, which is 7 to the power of 4 squared. Okay, and then I've got in here 7 to the power of 7, 7 to the power of 7 squared, which is, let's just write that, 7 to the power of 14, plus 7 to the power of 7 plus 1, and that's squared as well, so actually I've just got this all squared, right? So look, it's this squared minus this squared. 7 to the power of 4 squared is this 7 to the 8, and then I've got all of this stuff squared. Okay, so using the difference of two squares, it's just this plus this times this minus this. Right? So I've got 7 to the power of 7 plus 1 cubed plus 7 to the power of 4 times 7 to the power of 14 plus 7 to the power of 7 plus 1. That's my a plus b, multiplied by a minus b, which is 7 to the power of 7 plus 1, minus 7 to the power of 4 times 7 to the power of 14 plus 7 to the power of 7 plus 1. And that's it. Right? It says you should not attempt to calculate the answer explicitly, just leave it in terms of powers of 7. So I can leave it just like this. If you want, you could multiply out this a little bit to leave this as like 7 to the 18 or something, plus 7 to the 11 plus 7 to the 4. But in principle, at this point in the question, we are done. Right? We've answered the question, we've found the structure. This is some number, this is some number. When you multiply them together, you get this, and there we are. Okay, so that's the end of question 1 from this paper. It's taken us almost half an hour to get there, although I did do a bit of talking in between. But that's how long you've got to answer these questions. You do 6 of them in 3 hours, and you get incredible score on step, which very few will ever get close to full marks here. That's not the point. You're meant to just have a go at the problems and be able to give a good response to a few of the questions, and to try and pick the ones that you think you've got the best chance at. I will make some more videos like this as time goes on, adding some extra questions in, certainly doing some more question ones, also doing some other questions from later in the paper, and at some point perhaps we'll look at some step 2 and 3 as well. But we'll see how it goes. I'll see what response I get. So let me know what would be most useful to you if you are watching this, and I will see you in another video. Don't forget all of the resources, lots of A-level teaching resources, and for lower down as well at GCSE at the Mathsaurus website, which is linked below.